Rate equals K.
Oh, rate law.
Concentration rate.
K of A to the M times B to the A.
Okay, so that's the generic formula, right?
Yeah.
Okay, so now let's apply that to here. It's kind of simple because it's just A. It'll be A in brackets, right?
It will be
So go ahead.
B plus 2D to the other.
Remember, rate laws don't have products. What do they have, guys?
Oh.
Reactants.
Oh, just
So
A.
just A to the M.
All right, someone else want to try to jump in? Go ahead, Charles.
It's rate equal to K times the concentration of A.
And why is that?
Because it's first order, so A doesn't have any, like the exponent is 1.
Right. So and this question was kind of tailored for this, right? Because how many reactants do we have, Charles?
One. Just one.
Just one. See, that's part of the trick with this stuff is the overall order is what's told to us by this graph here.
Yeah.
And that can be tricky because M plus N get added together to give us the overall,
Yeah.
right? So the only one where you would really know even if there were multiple is if it was 0 ordered, right? Because the only way to get 0 is to add what plus what, guys? 0 plus 0, right? 1 could have been made with a 0 and a 1. But we're fortunate because they did give us this equation. So, Charles, would you like a peep or a brownie?
I'll take a brownie. Thanks.
Mr. White,
Good man.
I have a question.
Yes, sir.
So for this, you would use the equation Charles gave to find rate law, right? So when would you use the integrated rate law that we just learned? Like,
Great question. You can use it to find like concentrations and stuff like what we might even use it for part C there. We'll see if we have everything we
Dang,
need.
man.
Like it can actually be used, but to be honest with you, the most of the time it's used just with these graphs to know which one's which.
okay.
Like it can be used, and we will use it occasionally, but its principal value to us is in kind of the conceptual theory with these straight lines.
All right, that makes sense. Thank you.
All right, so let's just go through here. And was Charles correct officially?
Yes.
Good job, sir. Let's go through the official guidelines. So we knew it was first order reaction because a plot of the natural log of A versus T gives us a straight line. And A yielding B plus 2D tells us that the only reactant is going to be A. So that's really nifty because we know the overall order and we know that there's only one reactant. So therefore the overall order has to be the order of A, right? It's harder to really...
What fell?
That is the universe's April Fools on us. Obviously UF does not go in the trash. Obviously.
Of course not.
Yes, Victoria.
So we use the rate laws for the overall order of the reaction, right?
Well, yes, because remember, M plus N equals the overall.
Overall, okay.
But if there's only one reactant,
Then
it's just an
that's
M, and M is the overall order. Okay, so let's move on then. So part B wants us to find the rate constant. So guys, how do you think we could find the K? Go ahead, Rhea.
Okay, I think you're gonna solve it for K, so it's gonna be the time over the concentration of A. That was right here now.
What do you mean? Oh, you're already solving it. You're like a step ahead. I was going to say you plug them in and then,
Yeah.
okay, so you're already dividing them, okay. So, yes, now what they're showing us here is what Avi was saying, where we could use the overall integrated rate law.
Can we also just use the regular rate, the reactant?
I think so. Let's double check.
Because we're given times, we're given concentration.
Yes, sir. Let me
kinda
double
hard to see.
check.
But it's
here.
not consistent.
6, 6, and 10.
It goes down by
Oh, yeah, you would have to
0.3
go
and then
like-
goes down by another 0.3, but over way more time.
Hold on.
Wait, maybe?
No, yeah, because these are
Yeah.
increasing or decreasing by like 3, right?
And then,
Ish.
yeah, but like
Oh, but it doesn't matter because these could just be different numbers. So hold on. What was our rate law? KA.
It was KA, yeah.
So it would be, like Ria was saying, it would be rate over A.
Mm-hmm.
Oh, this is time though, not rate.
Yeah.
That's what undoes us.
Okay.
Yeah. You know what, Ria? I was on your train too, because I forgot. See, when you're doing a question, it'll all be on the paper in front of you.
Yeah.
But here it's on different slides. I forgot. I thought it had rate here,
Yeah.
but it's not rate. It's time. But you're still correct if it had been rate.
Yeah.
But so to answer Avi's question earlier, it is very useful when they don't give you the rate. This can let you cut out a step because see it involves time.
So if they're asking you to solve for rate constant, you use the integrated rate law if it's a first order equation.
Yeah, so if you don't have rates already,
Okay.
this is very nifty. Now if you have the rate, the regular rate law is much simpler, right? Like that.
Yeah, okay.
So,
Yes,
so
sir.
for that, like obviously, you use the integrated one there, but could you also just use the regular, like equals the negative change in concentration over the change in time?
Oh, absolutely.
Okay.
Yeah. And if you did that, you would then use this.
Yeah.
Exactly.
Okay.
It's just the way a lot of these questions are, and basically, in other words, the way this whole course is, there's a whole framework of truth, and you can kind of get yourself to different ways. It's like a Google Maps to somewhere.
Yeah.
There's many different ways to get to places, but there's generally a preferred way in a particular
'Cause, like,
question.
with the integrated one, it has K in it already. So
Exactly. Yeah.
Where's the negative sign go? It says negative KT equals the length. Where's it
they
go?
put it here.
Oh,
'Cause
I
they
somehow missed that.
divided negative t from both sides.
Okay, I'm going to take a bit of time to write this.
No worries. Take your time.
I thought that you were just saying earlier that we had to write as quickly as possible.
Well, I was trying to get as much done as we could before the drill,
Okay.
which turned out to be better than I was expecting, but not a ton before.
Why was it?
It
What
wasn't
were you
as long as
expecting?
Well, because it was supposed to be at 9:25, so I thought I would only get a minute done, but I ended up sneaking in like 7 minutes of stuff.
Would it not have been more efficient just to have everything in one bulk instead of broken up?
No, because we got some. It's always better to have something done.
Okay.
Because the code red was going to end whenever it was going to end, but we had some done before then. And even if my logic doesn't make sense, my logic is law in here, so that's all that matters, you know.
Oh, that's why it's seconds to the -1 because it's a rate.
Correct. It's per second.
Do we just pick a time and just said it's that now? Like was there any reason for picking 50?
Oh, because it's 50, right?
Because it's just the easiest, I guess.
or it's just
Yep,
one of them.
yeah, but like-
You could use any of them. It's convenient to use 0 as your initial,
Okay.
because then you literally just use whatever the number is of the final.
Okay. Just wondering.
Yeah.
Mr. Lloyd,
Yes,
how
sir.
was your day?
You know, my day's really good because any of you are Yu-Gi-Oh fans in here?
No.
I know, and I've played
I used to
Yu-Gi-Oh
watch the
before.
Wow,
I
so
don't have a lot.
Yu-Gi-Oh's really kind of fallen off then, huh?
Yeah, it has.
Yeah. Well, you guys know my primary interest is
Pokemon.
Pokemon, of course, right? But Yu-Gi-Oh still holds a special place in my heart. And this new cool box came out. It has 8 decks built in. It's for Yu-Gi-Oh Speed Duels. Yep. I'll play it with you guys sometime after the AP exams.
Wait, Mr. Lloyd,
Yes, sir.
on the flyer for the AP review, it says that teachers are supposed to, like, the AP review that's like Tommy's doing, it says, but teachers are supposed to get like the links if you do it online.
They haven't sent it to me
They
yet.
haven't sent it to you?
That's what I was waiting for before I blasted out to you guys. I was waiting to get that link
Okay.
because I didn't want to confuse you guys with like multiple things for it. This way, you'll know that the one for me has the link for it.
Do you think it's useful though? Like the AP
I mean, I think any second you spend that's not on Fortnite or Discord or whatever, that you're at least eyeballing and having AP Chem stuff passively going in you, I think it's a good thing, right? Obviously, high quality individual, like disciplined study is always the best. But for most people, it's really hard to achieve that with an academic Stop it. With an academic subject. And so as a result, that's why school exists. See, contrary to a lot of people, that's why in the pandemic, all the online stuff failed miserably with its goal. Now you could argue it succeeded with versus nothing. When you compare it to nothing, it did great, right? But when you compare it to real school, the online stuff just across the board, any objective measure was a complete failure. And that's because the human brain wants to do fun stuff. And that's the nice thing about school is it forces you to focus on the not fun stuff.
You can't just walk off and start playing a video game in your own house if you're at school.
All right, so anyway, let's move on here. So part C wants us to find A at 500 seconds. Oops. So again, we're going to use that integrated rate law because, you don't even need a rate. And now, in order to solve this, though, it is a little tricky because how do we get rid of the ln off of something? We have to take both sides eventually as powers of e. And that will solve it for us. So that is the one kind of where you do need a little bit of advanced math here, is you need to know how to get rid of ln's, and the cure to ln is e.
Oh God.
Can I get a peep now?
Where does the 0.003 come from?
What's that?
Where's the decimal come from? 0.003.
Oh, that's from the chart. Wait. Because that's initial.
It's
initial.
K. It's K.
Okay.
No, the 0.020 is initial.
Oh,
No, but you say 0.003.
Are you talking about the 3?
Yeah.
Oh, this is the K we just calculated. Oh, great point though. Let's say hypothetically you didn't know how to get K. You could just throw a random number down in your answer for the previous question and then put that number here and you could get the points.
Oh, I like that.
Remember, error carry forward, guys. Do not throw away points unless it's to get a point later on. Yes, sir.
Is this on a formula sheet?
Why, yes, it is. That's the cool thing is this is actually given to you on the formula sheet. Welcome, sir. Glad to have you. Would you like a peep?
What?
Usually if I show up late, I
A peep of what?
Of what?
This one.
Mr. What? Can you go back to the chart, like the chart? Okay, they said to use,
Talking about the 0.020?
yeah,
That's because we need time as 0 as the initial.
and then I got the ln of 0.020, but then we used,
Like, you have to add all this stuff up together and multiply, get this all together, and then e to that power. What's up, Avi?
I'm doing the math, but doesn't E and ln cancel? 'Cause, like,
that's
It
exactly
did
what I-
over here, but you have to e both sides.
0.02.
You have to e up both sides.
Oh, yeah.
And no, this doesn't cancel because this all gets resolved before you e it.
I would still give you that answer.
Okay.
Like this whole thing gets resolved before you e it.
Okay.
Like you have to actually do all this math first, or your calculator will do all this math. Highly recommended. You just let your calculator do it. Guys, don't forget when you're doing any sort of math, it's always better to have too many parentheses than too few. Okay. Because the calculators are generally actually pretty good about orders of operations, unless you've got the bad calculator. You know who you are if you have that one. The bad calculator. Oh, you have it, right? Oh, there it is! There it is, true evil!
Let me see.
What is it?
Hold it up.
Oh, here, like-
Doesn't do order of operations properly.
Boo.
It's okay though, you choose parentheses. It makes you stronger.
I just like do each by second and write it down.
It makes you stronger. You know, it accumulates all of those rounding errors and puts it all in one good package for you. Love it.
Got an A's like this for math stuff.
All right, so let's look at example 2 of first order reactions. Data from experiment which examined the change in concentration over time for a first order process at 25 Celsius was used to plot the graph below. Sketch a line that shows the approximate results that would be expected if this same experiment was repeated at a lower temperature. So you notice that we're going to put it up here like this. And that's because, and it's going to start at the same point here. And it starts at the same point because the concentration initially is going to be the same. However, it's going to be, it's going to diverge, and we're going to put it above the graph here. Okay? And the reason it's going to do that is because what does it say about the temperature right here, guys?
It's lower.
And this kind of touches on a point that we haven't entirely explored yet. But typically speaking, do you guys remember in thermochem how we learned that it depended whether or not it was endo or exothermic? You guys remember that?
Mm-hmm.
But remember, that stuff only decided whether or not it would happen. Kinetics, though, decides how quickly or fast it happens, right?
Yeah.
And the universal rule is if you want something to be faster,
You heat it up,
you heat it up, right? So this is talking about doing what with the temperature?
draining it away.
It's going down, right? So this does get a little weird, though, if it's an exothermic reaction. I will say that, okay? Because obviously exothermic doesn't like being heated up. All right, I am going to point that out there. But typically speaking, guys, if you want something to mix better, typically speaking, what do you do to it?
You heat it up.
And we heat it up because you get the particles moving faster. And chemistry is all about two particles doing what?
Stuff.
They have to collide. Can things react in chemistry if they don't touch? They must touch in chemistry. And it may not look like they are, but they are at the particle level. So that's why this is going to actually be a bit higher because, you know, when you do LNs, it does that. Okay. So now we're going to talk about half-life for first order reactions. So in a first order reaction, guys, the time that it takes for half of your concentration to be cut in, I guess I said that wrong. It's the time it takes for your concentration to be cut in half, not half to be cut. Your concentration to be cut in half is your half-life, which is T1 half. Now, on your reference sheets, there is a little cheat code. I'm going to show you the long way in a second, but I might as well just start with the cheat code because this is what you'll use most of the time.
T1 halves are the same,
That's why it's half-life.
but it will. But that means that it'll never run out of material, which is
Yeah, just like nuclear stuff. This is just like nuclear stuff.
what? I thought we were talking about like equilibrium things.
No. We are, but that's what I'm saying. It's just like nuclear science.
We're nuclear
Nature
scientists
repeats itself
now.
sometimes.
So if you had a lump,
concentrations of a first order reaction for the reactants, they get cut in half over a certain time. And then if you repeat that amount of time, you'll cut whatever you have in half.
and so if
And
you
you'll keep
had,
doing that until you reach kind of like an asymptote.
so you could, that's annoying.
So to find your half-life, guys, it's going to be equal, T1 half equals 0.693 divided by K, and that's on your reference sheet. Now we're going to do the long way, but that way it just, you literally just plug in your K. Or what could you also plug in? It's not just about finding K or T, I just gave the answer. What could we also find with this formula?
Okay.
K, ooh, backdoor K right there. All right, so this question's asking us to find the half-life for the following reaction. Oh, one thing I want to note real quick. just so you don't confuse it. What's this graph? What's on the y-axis here? Plain old concentration,
Yeah.
right? But what's on the axis here?
Linear constant. No, natural log concentration.
Natural log, right? But it is also linear, right? So, guys, what could you say already about this problem if it wasn't written up here?
First order.
First order. Is that what you were going to say, Solomon? Perfect. Okay. So, we need to find the half-life for the following reaction. And we've got our ln graph there. Yes, sir?
So, if to find the half-life, couldn't you just subtract the final initial and just divide that by 2? And then just subtract that from the initial?
So, Avi, what did we just talk about? What's on the axis here?
Numbers.
Numbers. Your molarity.
There's molarity here, but what's here?
The natural log.
Half-lives deal with regular concentrations.
Okay. So, okay.
Now, if it was a question where they gave you this, then you're right. You could just do that. Okay. Hey, welcome back. All right. So,
No.
step 1, we need to find K. And K can be found, here's the nifty thing, K can be found by finding the slope of, that's one of the values, guys. You might want to write this down. One of the values of knowing when it's a straight line is that your slope of the straight line is actually also your
Okay.
K. So when they give you the straight line, they're also basically giving you K. You just have to do, what's the old thing we learned for slope, guys? Rise over run.
Or do IDX. Well,
Hey, what's up?
Can you go back like one slide
Oh,
real
the
fast?
shortcut is T1/2 equals 0.693 divided by K. So T1/2 or half-life equals 0.693 divided by K. So that's 0.693 divided by K.
Can you go back like one slide really fast?
I have one more question.
Go ahead, Avi.
Okay. So, as this gives you the natural log of molarity,
I'm good, by the
to
way.
find the half-life, you said if I give you the actual molarity, you could do what I said, right? Where I just subtract the 2 and divide it by half, right?
I mean, you would still need a K is the issue.
Okay.
If you can get the K, then you can use our little lovely thing over here. But if you notice, when you're doing the long way that they're going to teach you how to do right here, you still need to find what?
Okay.
So, I mean, you need K no matter what. Might as well use the shortcut, right?
Yeah, fair enough.
But we'll get to that. We got to learn the long way first. So, the K then will be the slope. Oh, one thing though. We have to make it the negative slope. So instead of negative 1.70, it's going to be 1.70 times 10 to the negative 3. All right, guys. So it'll be 1.70 times 10 to the negative 3. All right. Give you guys a second here. Are you guys having a good day?
No. Yeah, I just woke up.
I am so glad it's Friday as well.
I'm having a
It
decent
doesn't
day.
feel, it doesn't feel like it one
A Friday?
It doesn't feel like
Yeah, it feels like a Tuesday.
Well, it has been a short week, so.
It feels like a Friday to me. All right, so the next thing is they're going to tell us here that they're going to tell us to do they're going to have us use the integrated first order rate law, and then we solve for t, get t by itself, and then we're going to plug the concentrations in as 1 for the final. I'm sorry, 1 is the initial because it's half-life, and 0.5 is the final. And then we divide it by the K. But here's the great thing, guys. If we're always going to do 1 and 0.5, this is always going to be the same number, right? Ergo. So you see, this is kind of showing you how this came about. So now that you've seen this, what are you guys always going to do?
that.
That one. Yeah.
So
But
does that
this
mean-
is showing you how the shortcut came about.
Does that mean in multiple choice questions we might have to remember that?
No, oh no, this is on the reference sheet.
That's on the, okay.
Oh.
This is on the reference sheet. That's why I'm saying College Board supports
Yeah, I was
this.
gonna ask if you had to prove it.
Yeah, no, this is definitely on the reference sheet. You've got first order integrated rate law, second order integrated rate law, and this for kinetics, and that's all they give you. But it's still pretty good they give you the first and the second order. And you'll know it's first order because it's the first one on the reference sheet, so that's first order.
Whoa.
Yeah.
And then the second one is obviously going to be your second order.
Is there a shortcut like this for second order?
We'll get there.
Okay.
But whenever you're doing half-life, it's always for first order.
Okay.
Because zero order is linear. So no need for
Guaranteed. Yeah.
Well, actually, there is no half-life because it's linear. Like, you always lose the same amount, you know. All right, so let's do an example together here, guys. Which of the following processes has the shorter half-life? Justify your answer. Oh, we could do this real quick, can't we?
Oh,
One.
Which one has the shorter half-life,
One.
guys?
One.
Why is that?
The
because
larger
K is
K.
bigger.
Because it'll be the bigger denominator in this one, right? So guys, to review, the shorter of these two choices is going to be number one, because where do we plug in the K to find half-life? Into this equation right here, 0.693 divided by K. When you have denominators, the smaller number answer will always be the one that has the denominator that is
Bigger.
bigger, in which case we pick number one. And so both processes are going to be first order, and process one occurs at a faster rate when both systems share the same initial concentrations as its rate constant has a larger magnitude. What's up, Solomon?
I was gonna say that it kind of makes sense too, because like the longer it goes, obviously the shorter it will take to cut in half. Not that, I don't know. Or like-
Remember, these are
Saying
Ks.
that wrong.
These are
Yeah.
Ks.
Oh, okay. Never mind.
Not, these aren't the actual rate, these are Ks. Now, one thing I will also point out, guys, this first bullet point says both processes are first order. How are they making that claim? How can you look at this chart and this question they give you? How can you look at this? Ignore this part up here because it's telling you. But if you ignore this part up here, how do we know from the blue part, including this graph right here, their chart, how do we know that it is first order? Go ahead, Santiago.
The rate law?
Okay, what about the rate law?
Like, you know how it has like the M and the N at the top?
And there's
Because-
just one
and there's
reactant
just
there.
one, yeah.
And it has obviously first power. Very good.
Power.
All right. Yay! Now we're doing second order.
No.
It's the same,
So
just
instead
with-
of ln's, we can integrate a second order because it would normally equal k to the a squared. Second order gets integrated and looks like this. 1 over the final concentration minus 1 over the initial concentration equals k times t. And where is this located? This will also be on your reference sheet. And it'll be the second one they list. So therefore, you should always know this is the second order.
Will we ever have to go farther than the second order for?
No. Like, we'll hear about the existence of it, and we'll discuss why it is both improbable and very uncommon to go beyond second order. We will discuss that.
Even in like big kid population.
You guys want me to just spoil it?
Yes.
Yes.
So the reason it doesn't really go beyond that is the orders correspond to how many particles are involved. Generically
So
speaking.
wait, why is there like a -1? Because I remember I was watching this like presentation and there was like 5 other orders that we weren't talking about. Or there was like 3.
Well, basically, what it comes down to is we're going to learn about what are called elementary steps. And
So the negative.
basically, guys, it's pretty normal for two things to collide, right? Right?
Yeah.
But how common is it in reality for 3 separate things to perfectly collide at the exact same time. It's always ever going to be two colliding, right? And then maybe a glancing blow on a third thing after they've already separated, right?
That's
even rarer, like.
Yeah. So in other words, the likelihood of more than two things colliding at the exact instant is very low.
What about the 1/2?
Huh?
1/2. There was
Good.
like a 1/2. And then
Anyway.
like a -1. Are we ever?
Anyway, moving on here, guys. So we can actually also rearrange this one. That totally looks like y equals ms plus b, right?
Yeah.
Totally.
Oh, yeah.
Yeah.
Kind
Okay.
So what's cool then is if you have a straight line and your y-axis is 1 over the concentration of A, then what order is it?
of
Second order. If your graph has a straight line and it just has concentration on the y-axis, what order is it?
zero.
0. If your graph has ln of concentration, what order is it? 1. Huh?
If it's a straight line, then
It has to be a straight line, and we look at the y-axis. What if it's a straight line and the y-axis says 1 over the concentration? Second order. Very good. There it is. 1 over the concentration straight line is a what order, guys? Second order. All right, any questions about this part? So guys, if they give you a bunch of graphs and 3 of them are curved and 1 of them is straight, which one are you going to look at?
Straight one.
Straight one. And what are your eyeballs going to really focus on in that particular graph with the straight line? Let's have someone new.
I have no idea what class this is right now. I'm so new.
Let's have someone new. No, Bianca, you already answered something earlier. You did a good job. Huh?
I don't know.
Wait, you don't know?
Can you repeat the question?
We have 4 graphs. 3 of the graphs have curves. 1 of them is a straight line. Which one are we focusing on? With the straight line. And when we zoom in on that one graph, what are we paying attention to try to figure out what order it is? Yes, we're looking for whether it has natural log, 1 over the concentration, or just the concentration by itself, which would tell us first, second, or 0 order, right? Go grab yourself a peek.
Taking so many notes.
Is that
How many
cookie
left?
still
Just
there?
one? Just one left?
Yeah, there's 2. Yeah.
Oh, there's 2 left?
There's 1 left now.
There's 1 left now.
Is that cookie still there?
Is it?
Squid game.
Yeah, the cookie's still there.
Okay.
I'll take it.
What exactly do I have to do to get that cookie?
Well, I have to be inspired by something. Oh, here we go. Here we go. For the peep and the cookie, who wants to come up to the board and try to solve this problem, and then we'll check it with the slideshow.
Dude, I was just talking about
We're
it.
just trying to get a peep all day.
I actually want the cookie.
Okay, I'm gonna have to have. Oh gosh.
What
Man,
if
now
it's-
there's so many people.
What if it's 2 people and one gets the cookie and one gets the peep?
But I'm not gonna do it.
each person is 1 part.
Yeah, you can do it.
Should we make this interesting?
Yes.
Of course.
We have 2 sides of the board, here and over here.
No.
We could have 2 people try to solve this in parallel. And the one who gets it done first and correctly.
No.
I'm interested.
I'm not interested
Vaguely.
Hold
anymore.
on, hold on.
I don't do
Hello,
well
this
under
is Mr.
pressure.
White.
Hence why I failed my AP test.
Hey, what's up?
What?
Damn.
Yes, why don't we take a quick break? What's up?
Wait, I really looked at the answer like in the examples on the PowerPoint, so just right here.
Nice.
So, I mean, it's not that hard anyway.
So, don't, she may already know, but don't tell her, but some of her classmates brought some stuff for her birthday today. Oh.
Whose birthday is it? Let's go tell her.
Why does
April Fools?
everyone have a birthday?
Fools me ate all your stuff.
Oh, absolutely, yeah. I think it's like 25, 26. Oh, no, this is fine. Yeah, no, I'm teaching AP Chem right now. They all have a sigh of relief right now, because I was just hitting them hard. Right, guys, I'm hitting you hard.
Yeah.
Yeah.
Oh, yeah.
Don't, they're screams for help, don't listen to those. Alright. No problem, thank you. Yes, I'm scoring donuts later. Well, it's a girl's birthday, but I'm just gonna score at least one donut. It's all about the skim, guys. It's all about the skim.
Mr. White, what period? I might squeeze by.
No need to worry about that. Okay. So,
Happy birthday.
we gotta start this gauntlet here. Who wants to solve this problem?
I do.
Oh my gosh.
What?
You know what? We'll give everyone the shot now.
What?
Oh.
How?
Here's what we'll do.
Get this answer.
Everyone, but we won't start yet. We're gonna have an even playing field. Everyone
Paper.
get their paper, or if you want to grab a board, like if you don't have paper, I don't know why you wouldn't have paper. But everyone get your paper out. No one start yet. We're all gonna try, or actually, no pressure. Those who want to take on the challenge will start. When I say we'll all start at the same time, you'll try to solve this problem in its entirety, and then you will
Wow.
line up so that
I'm
we
just
can
writing
just
the problem
establish who gets checked first. We'll do a lineup, and then we will grade it and see who gets. Maybe should we do a first and second place scenario?
Yeah.
Yeah.
Okay, so first place chooses Cookie or Pete. Second place gets Cookie or Pete. That's left over. All right? And if you don't want to participate, I don't know why you wouldn't. This is fun. Go!
I'll give it to someone else.
And remember, the lineup starts here.
I don't like sweets.
Well, you can still try. Spirit of competition.
Alright, it's gonna be your professional. You have to do it.
And I'm loving the competitive vibe in here. This is great.
How do you have both already?
Did you start like right when he said?
How?
Rate log easy.
Well, okay, yeah, but like you gotta do both.
Put it in my
Damn.
No, don't give up. She could be wrong.
I'm not saying I'm giving up. I'm saying that I'm probably not doing this.
Mr. White, can you use a calculator real quick?
Yeah, here.
calculator.
But you will have to back away a couple steps in case someone like solves it before you finish the search.
Oh yeah.
Just for fairness, you know.
Mine? Solomon's are whiteboard.
Alright,
Anyway, I can't say it, because I don't want to like keep it out. Are you done? Are you going? I'm not going.
I can't
Can
find
you move,
natural
please?
I can't find
Someone?
natural log on my
Thank you.
calculator. I'm doing very good.
Oh man, tensions are high. Tensions are high. Okay. Okay. I don't know off the top of my head because I haven't
Can I
typed
see
in
what
the
you
calculator yet.
0.0.
Yeah, you guys can look because you guys are 1 and 2.
Is this correct?
All divided by.
I don't don't know the exact number yet, but make sure
I'm
you
so
stay in
dumb.
line.
I'm so dumb. I just
Guys,
pressed
stay in line
erase.
in case these two.
I think it's 0.5. Seven
We surrounded.
Divided by.
It's on the, like I put the PowerPoint up on
Is that what you
the.
wanted to round up in the
Huh? No, you're fine. You're fine. You
You got the right number.
Yeah. Hey, we're gonna put it up here, guys. Okay, so you two are first in line, right? Let's take a look, guys. So we find the rate law, and we know, guys, that it is a second order reaction because the straight line has what on the y-axis?
1 over and 1 over t.
And then this one's fairly straightforward because how many reactants do we have? Just
One.
And so that one reactant will be to what power in the rate law? The second power. And remember, a proper rate law is rate equals K times your concentration to whatever order.
Yeah. That was
Very
easy.
good. Okay, next, to find the K, we're going to use the data for T equals 0 and some other time, okay? Which means you have to use the 0.015 and the 0.070 from this chart right here.
Mr. White, I ended up with the right K, but I got it negative for some reason.
Did you get?
Then you
did
erase the
put a
negative sign.
K?
Oh, you didn't subtract these properly. You did this one minus this one probably.
Oh, yeah, that makes sense. Okay.
And don't worry, that happens a lot, you know. Okay, so thank you. My first 1 and 2. If you want to grab Rhea, you choose because you're first. The cookie's under the peep if you want the cookie.
Very sad.
Congratulations. Congratulations. That was a fun little contest, right?
Sure.
Rhea, I'm so proud of you.
No one agrees.
And Solomon, I'm so proud of you.
Why?
Huh? And I'm proud of you too.
Thank you.
And I'm proud of Charles and everyone else. All right. So, does everyone understand what we did here? Anyone need a clarification? Yes, sir.
Can you please
Can I do what?
can you please go through the process?
Yeah, so basically, we had to figure out that it's second order first. And we knew that it was second order because they gave us 2 graphs. Now, they tried to trick you guys. Tell me how did they try to trick us? How many graphs did they put on here?
2.
Oh, and what does this graph have on its y-axis? ln. And they even, they're so sneaky, they even made this one not like super curvy, right? But it isn't entirely straight. So that's why we knew to look at which one, the one with the very straight line, okay? And what does the one with the straight line have on its y-axis? 1 over the concentration. So that's how we knew it was second order. We combined that piece of knowledge with the fact that there's only one reactant from this equation, which means then that the rate law is going to involve that one reactant going to the second power. Now we have the rate law. Okay, that answers this one. This one, though, wants to know what the K is. Now, as we've previously discussed in this class, you could use this to find the K if you knew the rate for a given concentration, but we don't. So, or at least not yet. So instead, we'll just use this second order integrated rate law, which is okay because what order is this? Second. That's why we use this one. If it was first order, which one would we use? The ln one, right? So then we plug in the values of when t is 0, the concentration, and when t is whatever other time we want. We do all that, we plug it in, and we solve for the k, and that's how we get this as our k value. All right? Oh, and in case any of you are wondering from like a math unit perspective, why this k, second order k, has an m on the bottom to the -1, it's because what is anything squared, guys? A unit squared will also be itself squared, so it would be molarity squared, which we can't have in our rate. So how do we get rid of molarity squared? What are we going to put on the bottom of our constant? We'll put an m, that way we can clean it up. Because remember, rate law is supposed to equal, all this is supposed to equal what, guys? The rate. So that's what K is designed to do. Okay, let's do another example here. Data from an experiment, did anyone still need this one? Okay. Data from an experiment which examined the change in concentration over time for a second order process at 25 Celsius was used to plot the graph below. Sketch a line that shows the approximate results that would be expected if the same experiment was repeated at a higher temperature. So the line is going to be higher than the graph. The answer is higher because at a higher temperature, the rate of collision should be faster. And we'll talk about that stuff a lot more in the third kinetics, the kind of the conceptual stuff. And so as a result, you're gonna decrease AB faster. And guys, it's so weird, it's counterintuitive, right? Because when a reaction is going faster, you are using up, in other words, you are losing your reactant faster. But it's not the concentration of the reactant on the y-axis. What's on the y-axis, guys?
1 over.
1 over. So when you are decreasing something, but it's 1 over it, you are actually,
Going up.
and that's why second order plots typically go up.
So just understand, second order plots go up because it's 1 over your molarity.
Because it's 1 over the molarity of the reactants that are normally going down. Is this the last one?
Yeah.
Hopefully.
Oh my gosh, we actually finished one early.
Are we gonna go
That
over
is
the
not-
X's and bases?